I'm here to talk about continental glaciation, but you need to realize that mountain glaciation has existed forever. But we're talking about continental wide ones, and one of the preconditions for continental glaciation is that the continents have to be in a polar position, and polar, and that there's enough elevation for the snow to start snow, and then ultimately ice start to accumulate. So I don't know if you've ever seen this slide before. I find it intriguing. There's about 6 different talks buried in this thing. But this is the zero line, and this is a change in temperature from basically the norm, and the norm is established by the temperatures that you see in here. I get to use my pointer. You can tell I haven't done this. So you can see that we're starting back here in the Cambrian. The scale changes. This is 100 million years. Then we go down to a 500,000, somewhere in that neighborhood. This is a 5,000 interval. And then we go back down into 10,000 years ago, just to make you aware. And you can see that there have been some cold periods. One especially is this one down here in the Pennsylvania Permian, and definitely a glacial period. There's others. There's even evidence of glaciation in the Precambrian, Archean, and you can see that this is when Antarctica was covered with ice. It melted and went back into glaciation again. This is a trend for over the last 5 million years, and here's the last 500,000 years. And what I'm going to try and do is explain this periodicity that you see here of a glacier approximately every 100,000 years. And obviously, the history has been that our climate has been cooling continuously all the way up to the present. So we'll talk about global warming here. Okay. Oh. So, at any rate, this is the pole position of Gondwana land during the Pennsylvania and Permian, and this shows striation directions, which you can find, for instance, in India or over in South America. And this is the kind of evidence you find for these late Paleozoic glaciations of Gondwana land. Here's tillites. Tillites kind of looks like a rock that has plums in a pudding, simply because there is no stratification, in it. It's just dumped material from the glacier, glacial striations, and then drop stones. And these are drop stones that result from the rocks being picked up underneath icebergs when they move off of the continent. And then subsequently the bottom of the iceberg melts and these big boulders drop down. Here's, we're talking about ice sheets. This part I'm not going to deal with for a second, but this part here is what our modern conditions are concerned. We have only continental glaciations like Antarctica and Greenland, where the terminus, the ice just actually moves out in this direction and breaks off and floats away. So this is the zone here where you're accumulating material, and this is the zone where you're losing material. But this marine margin types of continental glaciation limits the extent at which the glacier moves, limits it in the sense that it doesn't go past the shoreline. So this is just a shot showing you Greenland and the sea ice in the Arctic here. you can see that it's pretty well a marine margin glacier. Here's a little bit of land that's exposed, but basically it is a marine margin glacier. And this is two cross sections across the the Antarctic sheet and Greenland sheet. Two things I want to point out is that here is the crust, and if you instantaneously melted all the ice away, Antarctica would be a series of little islands. It's below sea level. But the other point I want to make is that ice can stand in the vertical for 4,000 meters, which means that's, if you plotted it in miles, it's about 2.5 miles thick. And what I'm trying to do is I'm trying to present you a model. And so as a consequence, I'm trying to pick up numbers from existing conditions to try and put it back into a context of why we have a periodicity of glaciers of about 100,000 years. I'm going to put together a model. So that's an important point, that in fact ice will stack up for 4,000 meters. Now, what I want to do is I want to talk about this side of the glacier, where we have land-based glaciers. The terminus is on land, and it's continuous land, it's infinite land. So this glacier, depending on its dynamics, if there's enough ice being generated up here, snow and ice, then the budget is such that this glacial front just keeps moving further and further. And we don't see that. We don't have even a model of that on Earth today. So that changes the dynamics of my concept of how that 100,000 year period comes in. Another thing you need to know is that when you stack ice up on a large sheet of ice, let's say this is 4,000 meters, on the continental crust, the crust begins to sink due to isostasy. If I have 4,000 meters of ice right here, then the crust will sink about 1,000 meters. That's the ratio. And the displacement of the material on the bottom underneath actually moves laterally, and it pushes up the Earth's crust on either side. This is anywhere from the ice front, anywhere from 100 to 300 kilometers, and the height in here is about 100 kilometers. This is highly exaggerated, but what this does is it creates some phenomenon like when the ice is melting here, it banks up the water, and you can have large lakes, and we can also have rivers that flow along the base of the ice. So here is a glaciation of North America. You can see up here that it managed to come down to a latitude of somewhere in the neighborhood of 45 degrees in that neighborhood. There are a couple of big sheets that is broken up into sheets: the Greenland sheet, the Laurentide sheet, and the Cordilleran sheet. This is Wisconsin glaciation, which is the most recent, but there are some earlier glaciations that actually extruded further down. But we're talking a great distance for this ice to have moved. Several other different things. Since we stacked all this seawater up here in the form of fresh water, sea level dropped, and as a result, this is the shoreline during the maximum glaciation 18,000 years ago, or 18,000 years ago. And what we have is we have ice margin phenomenon like lakes, large lakes in here. The Great Lakes actually were generated as the ice retreated. And so if you know anything about your rivers, this is the Missouri River coming down like this, and this is the Ohio River here, and the water came together and moved out down the Mississippi. So things you see on a map are controlled in many cases. This is, I want to talk about another concept that we know that the continental glaciers can get down to 45 degrees latitude. They can be 4,000 feet thick or greater. We don't know how great it could be. And this is just a mountain glacier that I wanted to use. This is the equilibrium line. This is the 0 degree isotherm. Everything above this point right here is colder. Everything down below this point is warmer than 0 degrees. So the ice at this point is melting. It's a zone of ablation. And the moisture that's coming up here is accumulating in the form of snow and ice. And it's important because that is part of the construct of this model. Here's an example of it. I don't know how much you had in geomorphology, but here is the zero line isotherm. Here's the accumulation up in here. And down here, the melting is occurring of the ice. The ice is moving forward in this direction. Should realize that if the accumulation is greater than the ablation, then the glacial front moves down the mountainside or out. On the other hand, if the accumulation is equal to the ablation, then you have a standstill for the glacial front, and the glacial front will actually retreat. Really doesn't retreat. The ice is always moving in this direction. You melt the glacier back like this. So we talk about the retreat of a glacial front when the ablation is greater than the accumulation. The other thing I want you to note is this is a cirque. This is the birthplace of the glacier, and we're really talking about a plane that comes across this glacier. Everything above it is accumulation, everything down below it is ablation. So if we look at snow lines today, here is the 0 degree isotherm. All land masses above the 0 degree isotherm are covered in ice, and below it, the snow doesn't exist, or it doesn't exist throughout the year. Notice that this keeps getting higher and higher, 0 degree isotherm, and as you go in the polar regions, it finally intersects the polar region, and then permanent snow and ice are found out in this area. Here we have polar regions, the 0 degree isotherm. The snow line is anywhere from 0 to 66 meters. Down in here in the temperate zone, 1,000 to 5,000, and in the equatorial region, it is greater than 5,000. So this is the concept I'm trying to develop, but that is present day snow lines, and the 0 degree isotherm is much higher than in the past. Here's a glacial cirque right in here, and right now it has no snow or ice. This will melt off in the summer. So the 0 degree isotherm is above these mountaintops. And so this is down in an area where it's warmer and no snow is going to accumulate, and above it, somewhere up here, is going to be colder than 0. But during the ice ages, during the Pleistocene, the 0 degree isotherm had to be somewhere down here, and this area collected snow and ultimately ice. So the floor of these cirques represent a quasi-isotherm line, and as a consequence we can reconstruct the 0 degree isotherm for the Pleistocene. And here is a diagram that shows you latitude, mean cirque elevation, right here. That's the floor of the cirque. And then a 0 degree isotherm that's constructed on that basis, where as you go towards the equator, as you saw, that the elevation of the 0 degree isotherm keeps getting higher and higher, and then it goes down on the other side to the south. What I have is I have some data that says at 45 degrees, the 0 degree isotherm is somewhere between 25 and 3,000 meters. So now I've got a working model. I've got a slope for that 0 degree isotherm, as well as an endpoint elevation at 45 degrees latitude. So that's part of the model again. This is a diagram that shows the present day snow line, and here's the 0 degree isotherm. And notice right here, the 0 degree isotherm, the land masses of the tops of Appalachian Mountains were above 0 degree isotherm, so there were glaciers in here. The Appalachians had glaciers during the last glaciation, and then the 0 degree isotherm intersects the land mass here. Here's this Laurentide Plateau. The 0 degree isotherm intersects the land surface, so all of this up through here and continue on up here, this color blue was an ice field, or at least a permanent snow field, and ultimately generating ice. So that's part of the model. Then we need to touch some other things, because these are part of this model, and there are glaciation proxies that show the character of glaciation and interglaciation. You've seen that already on that first slide, or second slide. One, you can look at the carbon dioxide content in ice cores, and you can, in the void zone, and you can look at the oxygen isotopes in sea level, or in seawater. And the reality is there are two types of oxygen isotope. This is the lighter one right here. This is the heavier one. Seawater is made up of 99.8% 16, oxygen 16, whereas oxygen 18 is just less than 0.2%. And this is important because you have fractionation of water by evaporation, and what that means is that water molecules that have heavier isotopes will not be picked up in evaporation as easily as the lighter isotopes. Why is that? You have to put more energy into the water molecule to get it above the water surface. So that's basically what I was telling you here. Well, how does this work? Well, what we find is that we can use proxies that utilize the oxygen in the ocean. These are 4-ams, and they are calcium carbonate. This oxygen right here you can analyze and find out what the oxygen 16 to 18 content is in these shells. So, yeah, got ahead of myself. So what this preferential pickup means is that in the present day, evaporation removes oxygen 16 water, takes it up to the mountains, it rains, water flows down the mountainside as rivers. The rivers have a higher oxygen 16 content in the waters than the ocean, then subsequently it flows back to the ocean and mixes again. But here's where the hook is. If you have oxygen 16 being picked up during evaporation, and you take it up and you leave it in the glaciers, and you never get back to the ocean, then slowly but surely, the oxygen 18 content of the ocean is going to start to rise. And since these organisms utilize that oxygen in their shell material, It means that if you find animals and look at their shell material and it has a higher oxygen 18 content than normal, that means that they were living in a glacial period. And if the oxygen content is less than 16, or the oxygen 18 content is lower in number, then it's an interglacial. So this is where we get to. Here is two cores, one taken out of the Pacific, one taken out of the Atlantic. These are marine cores. This is 5,000 years before the present, but you need to realize that this is the surface and we're going deeper and deeper down into the core. And when you analyze these shells, you find that here the oxygen 18 is higher, here the oxygen 18 is less. And so this must mean this is an interglacial, when the ice melts and all the water comes back into the ocean. And this must be a time when all the oxygen 16 is stacked up into a glacier. So the oxygen 18 that's being picked up by the organisms is of a higher content. So this is the recent, and you can see here's the direction we're going. This is maximum glaciation that happened to occur at about 11,500 years ago. And this is the warming trend that takes us into the modern day interglacial. Here's the next interglacial right here. And look at this is the change from an interglacial to a glacial period. The slopes of the lines are two different angles. That means that it takes about 100,000 years for a glacial to establish itself, and then only about 10,000 years for an interglacial. Why is that? Can we explain it? So we go from interglacial, this is glacial period, there's the next interglacial, another interglacial, and then down into the glaciation. And you notice that these peaks are all about the same distance, which means that it's about 100,000 years, plus or minus 20 or 30. The last interglacial occurred 120,000 years ago. So that's a piece of proof of the character of the glaciation, continental glaciation. That is a slow descent into a deep glacial period and then a rapid ascent out of it. So it's telling me something about this model has to incorporate that. This is, we're going to look at carbon dioxide now in ice cores. This is an ice core from Greenland. And you see it's got stratification to it. Part of that stratification is, I'm going to misrepresent this to some extent, is part of yearly accumulations. Plus, some of the stratification is the result of dust and volcanic ash and things like that. So if you have volcanic ash in here, you can certainly age date it, potassium argon dating or argon argon. And here is just a small slice out of here. You can see the character of the stratification. And keep in mind that it's partly dust that's providing that. You are aware that during the glaciation, the climate is very dry out in front of the glacier because all the moisture is being incorporated into the glacier. So there's lots of dust storms. And this is just a slice of the core right here, and these are all the bubble holes that are in. Bubble holes that contain the gas at the time when this ice formed. So if we look at and analyze for CO2 in parts per million, here is the recent. The recent jumps around. Sometimes it's over here, sometimes it's here. Here's the interglacial, and here is the descent from the last interglacial into the glacial period. This is 11,500 years ago, and you can see that during the interglacial, the carbon dioxide content in the bubble holes is much higher than during the glacial period. And that's just the greenhouse gas effect. So more greenhouse, more carbon dioxide, the warmer the climate's going to be. Excuse me. So you can see the same signature. Interglacial, descend into glaciation. Interglacial, descend into glaciation. This sawtooth pattern is duplicated both in carbon dioxide as well as oxygen 16-18 ratios, and in fact it's duplicated in a variety of other gases as well. I just don't want to get into it. Howard, you haven't pushed it, pointed to your watch yet, so I must be doing all right.
Giving you a break.
So here is oxygen 16 ratios, oxygen 16 to 18 ratios right here. Higher oxygen 18 during this time. This is the cold periods. This is the interglacials right up in here. And then what they did is, this is almost the drawing of carbon dioxide, but I'm misrepresenting it, the red here, because in fact, this thing is determined by the amount of deuterium in the ice, in those various layers. And so they can apply a temperature value to those. This is a temperature value of a mean. Right here, this is a 0, and this is greater than the temperature of our past 150 years, and this is lower. So I brought this because I knew I'd run out of gas. So is this starting to make sense? Okay, well, I'm just trying to put together a model. That's all I'm trying to do. I won't ask Howard if it does, because he'll just give me a raft of crap. So this is the last 5 million years, somewhere in that neighborhood. Here's this 0 degree isotherm again, or not 0 degree isotherm. This is the average temperature of the last 150 years, and everything's compared to it. So you can see this plunge of temperature all the way to the recent. And what is notable is that from here to here, these glacials and interglacials have a 100,000 year cycle. But prior to that, it had a 41,000 year cycle. That is very difficult to explain. So I'm not going to talk about this stuff over here. So we go to Milankovitch curves, and I'm sure you've heard of them before. This is the amount that is the amount of, what he did is he calculated the amount of insulation coming into the Earth's surface, which is just basically energy. You can see this is the English watts per square meter, and you can understand that if this is a quantity of energy, it's spread over this distance in the equatorial regions, whereas the same quantity of energy is spread over a much greater surface. So the amount of energy falling per square meter, square meter on the Earth's surface is less in the polar regions, just as it's colder up there because of the sun angle. So Milankovitch had heard rumblings from a variety of different read about the concept of glaciation may be the result of the perturbations of the Earth and what the Earth does over time. And there was never enough data as to what the Earth really did in terms of its cycles, and there was not enough manpower to calculate the thing. So it sat around until Milankovitch, who's a Serb, who around 1940, decided he was going to tackle this thing. And so if you look at the Earth, right now the pole is pointing towards the North Star, but it will move around like this, and then ultimately the pole will be pointing towards Vega. And what it does is it takes 22,000 years to make that cycle. That's the periodicity of the precession. Right now, the Earth is angle is 21.5 degrees. At least it was when I was teaching. It may have changed by now, but it ranges all the way from 22.1 degrees to 24.5 degrees, and this swing from this position to here and then back again is a 41,000 year period. And then the Earth goes around the sun, and sometimes it has a circular orbit, sometimes it has a little bit of an elliptical orbit. And so for the Earth, at this position, it will move to this position, a circular orbit, and back out again. That's a 100,000 year period. So all of these things, if you think about them, the tilt of the Earth, this tilt especially, you're talking about a more intense sun hitting the polar regions. One would think that if the Earth is closer to the sun in a more circular orbit, it would be warmer and cooler away out here, and this plays a role too in terms of where the pole is during these cycles. So here, this is just confusing as hell, but what it's doing is it's showing the history of the Earth all the way back to 1 million years, and this is the precession, flopping back and forth. And it's also got some secondary waves in it, because you look at this, it looks like it goes like that. So as a result, I've used 22,000 years, but there's a 19,000 year cycle and a 24,000 year cycle. And the obliquity is the 41,000 year cycle. Now you have to realize that these two are interacting with each other. So there is constructive and destructive interference of the temperatures as a result of it. This is what hangs up everybody, and that's eccentricity, because if you look at it, it has a periodicity of about 100,000 years, from a glacial to an interglacial. But if you calculate out the insulation of the Earth, this is the history of it, from going colder to warmer to colder. And then you compare it to the glaciations that we already know about. Let's see, this is the present, this is the last interglacial, here's the present interglacial. And you look at this, it doesn't match up with a damn thing. So the question becomes, is there anything to Milankovich's curves except the fact that this has a 100,000 year cycle? Well, the reality is that, so here's what we're looking at. We're seeing this cycle that certainly represents obliquity, and then we're looking at a 100,000 year cycle, and it's eccentricity. But I'll go on. So here we do have several different things that we are looking at. First of all, solar forcing and glacial periods, stages don't match